This first guy here is talking about the gradient of f at 2 comma negative 1. Remember, gradient points to the fastest increasing direction. So in other words, you're trying to figure out what's the fastest increasing direction if you're located at 2 comma negative 1. Right? First, gradient is defined as just taking partial derivatives and making as vectors. If you differentiate this by x, what do you get? 2xy. If you differentiate this by y, what do you get?
X squared.
Just x squared. Right? We're doing partial derivatives, so you're considering these as constants. So for example, if you're differentiating x squared y by y, since this is a constant multiple, you can bring this outside, and then you're just differentiating y by y, which is just 1, right? So that's why it gives you x squared. That's where this x squared comes from. Okay. Hopefully that's okay. Okay, but then it's asking for gradient of f 2 comma negative 1. So what is that? Gradient of f 2 comma negative 1. That means I plug in xs. Into x, what do I plug in? 2. And into y, what do I plug in? Negative 1. So any x that you see should be replaced by 2. Any y that you see should be replaced by negative 1. So you have 2 times 2, negative 1, and then 2 squared, which is negative 4 comma 4. Okay. So that negative 4 comma 4 is the direction where the function increases the fastest. So that's the answer to part A. Now for B, we use the formula that the directional derivative, if you want to know the direction of rate of change, if you want to know the directional rate of change of the function f as you go in the direction of this unit vector u, you simply have to calculate the gradient of f dotted with that vector. Okay? And since we just calculate the gradient to be negative 4 comma 4, and then we did the we have the u hat to be negative 1/2 comma radical 3 over 2. That's going to be negative 4 times negative 1/2 plus 4 times radical 3 over 2, because dot product means you multiply individual coordinates and you add, right? Negative negative is positive. 4 divided by 2 is 2. 4 divided by 2 is 2. So that's what you get for B. Okay, so up to that point, it's pretty straightforward, except now you're being asked to find the second derivative in the direction of u hat. Okay? So one way to think about this is like, this is as if you are moving at 2 comma negative 1 in this direction, and you're looking for the second derivative. So, sometimes it's good to have a plan B. Let's say I taught you how to do this, but you forgot, and you just want to figure this out from first principles. So let me show you how that's done. So think about this trajectory where you begin here and you move in that direction. So you're saying your x and y, you begin at 2 and negative 1. So this is an alternate solution, which is not the one that I want you to do, but it's kind of self-explanatory, so you might have a better way to understand it. It's not the easier one to calculate, but it's something worthwhile. Okay? So you have x equals to 2 and y equals to negative 1, and then you're moving in the direction of negative 1/2 and positive radical 3 over 2, so you multiply this t, and that's the equation for the point particle that's moving along the line, starting at 2 comma negative 1, and you're moving in this direction of u. Okay? And what this is asking you to do is you want to find the second derivative, which is like the concavity at t equals to 0. That's what this question is asking you to. Is that okay?
Can you explain x and y again? Like, why you plugged in 2 and negative.
Oh yeah, when t is 0, where are you at?
2.
2 comma
Oh,
negative 1, exactly at this place. That's where you're at, right?
yeah.
Okay. When t is 1, where are you at? 2 minus 1/2 and negative 1 plus radical 3 over 2. So what is that? Here's 2 comma negative 1, and u is actually this direction. Okay, so let's say this direction. Here's the vector u, and here is this point 2 minus 1/2 negative 1 plus radical 3 over 2. So you're moving this way. So this t makes it every time time passes on, you're incrementing by this much amount of vectors. So you continue to move that way. Now this question is asking, what is the concavity right here? Like, is it smiley or like that, or is it very smiley or very frowning? That's what we want to know. Okay? Does that make sense?
Mm-hmm.
Okay. So now what you want to do is you want to plug this in here, which means that so usually what people do is like they write that RT is 2 minus 1/2 t and negative 1 plus radical 3 over 2t, just like that. They write a single vector version of this trajectory. So writing it this way or writing that way is the same thing. Okay. So write it like this, and then say, what is f of r of t? That's going to be x squared times y, but x is 2 minus 1/2 t, and then y is negative 1 plus radical 3 over 2t. And then what you want to think about is, now think of this as a function of t, and you're really asking for f double prime of 0. That's the question, okay? Yeah, it's as I said, it's not the most efficient way to do it. But let's try differentiating this. To differentiate this once, you need the product rule, right? So f prime of t would be 2 times 2 minus 1/2 t times 2, negative 1 plus radical 3 over 2t, plus 2 minus 1/2 t squared times radical 3 over 2. Now what I did was I have to differentiate this first. See, I'm using the product rule, right? So if you have p times q prime, that's p prime q plus p q prime. You know the product rule? Everyone knows the product rule, right? But when you differentiate this function nests inside the square function, so you have to use the chain rule. So 2 comes down, and then, oh, it's not 2, it's 1/2. Negative 1/2. Negative 1/2 is the derivative of the inside function, okay? Okay. All right, so that's going to give us like 2 minus 1/2 t. This is negative 1, so let's multiply it here. It's positive 1 minus radical 3 over 2t. And then plus 2 minus 1/2 t times 2 minus 1/2 t times radical 3 over 2. Okay, and now we have to differentiate this yet one more time, okay? So if I differentiate this again, then this is a product rule and that's another product rule. So we have to do product rule twice. Differentiating this gives you negative 1/2. Yeah, so the calculation this way is quite painful, so I apologize. So that's what you get by differentiating the first guy. And for the second guy, negative 1/2. Actually, I didn't need to write it like that. I could have done, let's write it like this. Okay, so you have 2 minus 1/2 t. Very cool. 2 plus 2 minus 1 half t. Okay, so that's what we get. But we just need f double prime of 0, so let's now plug in 0, which gives you negative 1 half minus radical 3. Looking at what happens. Minus radical 3 over 2. Yeah, when I plug in 0, that's another minus. So you get 1 half minus 2 radical 3. Okay, so that's what you get. Yeah, so the calculation was a bit confusing because we had to do a lot of product rule and chain rule. But this is like not something that hard if you did well in calculus 1, okay? So if you had no trouble finding derivatives in calculus 1, this is like still a valid way to do it, okay? All right, but let's try to solve this in a different way, which is less calculation. I guess the problem was that once we had du hat of n at 2 comma negative 1, what was the answer? I forgot. The answer to b. What was it?
2 plus 2 plus 3.
2 red 3?
Yes.
Yeah, okay. Once you get this, then you can't differentiate anymore because if you differentiate a constant, it gives you 0, right? So in order to differentiate again and then plug in 2, negative 1, you need to find something that doesn't have 2 and negative 1 plugged in. So you need this. You need this quantity at any x comma y. So the way we do that is by still using this formula, but we don't plug in anything to gradient of f. We use this itself. So 2xy comma x squared, and we do a dot product with negative 1 half and radical 3 over 2, which gives you negative 1 half times this would be negative xy. And then this time this was radical 3 over 2 times x squared. That's the directional derivative at any point. But this is again some function. It's a multivariable function, right? So having it this way now allows you to do another directional derivative, which, if you insist you want to write down what it means, it's always, you take the gradient of this and do a dot product with u hat. Okay. Yeah, it looks ugly, but what I'm trying to say is that you simply take the gradient of this and do a dot product. That's all you do. What's the gradient of this? Well, you still have to do the partial derivatives. Differentiating this by x gives you a negative y plus radical 3x. And then differentiating this by y just simply gives you negative x. And you have to do the dot product with negative 1 half and radical 3 over 2. Which is equal to negative 1 half times this is positive 1 half y minus 1 half radical 3x. And then this times this gives you minus 1 half radical 3x. Okay? So I just did the dot product. Dot product means component-wise multiplication. This times this, and this times this. Okay? So I got the first two terms by doing this times this, and the last one is this times that. Okay? That's what I wrote down. Is that okay? Are you following? All right. And then, since now I have the second derivative, now I can easily plug in the value 2 comma negative 1 into this function so that anytime you see a y that's replaced by this value, negative 1, anytime you see an x, you replace that value by 2. And these cancel, so you get negative 1/2 minus radical 3. Oh, so I must have made a mistake somewhere. Yeah. Okay, so that's the answer. Let me just make sure that what I have makes sense. Yeah. So since they don't agree, this must have been, oh, there is a minus. I forgot this minus. Okay, so they do agree. Okay, good. Yeah. I thought I made a mistake somewhere earlier, but this is minus 1/2, so this is minus 1/2. So they do agree, right?